Hello, everyone. Welcome to another thrilling Science Sunday. I'm predicting this is going to be thrilling, even though we just got here.
It's good to see you on a nice, bright blue sky day.
Yeah.
Joanne was a little bit concerned about some large object in the sky, but...
Bright and shining ball of hydrogen.
Right.
Yeah, we haven't seen that in a while. Apparently it's going to go away again, too. It's supposed to be really cold this week, so everybody take care, stay warm, and as you go about your holiday festivities. Let's see. Last year, I gave a talk about cosmic ornaments, and I had a lot of fun putting that together. This year, we have a house full of about 7 different people coming and going. Kind of have a...
At your home.
At my home,
Right,
yeah.
we have about 7 people here as well, too. So
Yeah.
welcome to everybody, and thanks for coming in.
It's a lot like being at home, so I feel comfortable.
All right, good.
And we have nice audience here today. And anyway, that's all preamble for the fact that I may not have as many special effects in my presentation today because I've had limited time to work on it, cooking and cleaning and entertaining a bunch of different guests. So if there's any glitches in my slides, I blame all of my house guests. So anyway, I had fun last year doing the cosmic ornaments, talking about some of the most beautiful things in the sky. And I thought it would be prudent to talk this year about some additional cosmic ornaments that have been unveiled, as it were, by the activities of the Webb Space Telescope. I think you talked about the Webb Telescope
Right.
about a year ago.
Yeah.
And I think the Webb Telescope itself launched exactly 1 week from today, last year. So it launched on Christmas Day last year. A great Christmas present to all of those of us who are interested in astrophysics and pretty pictures and comprehending the universe in an ever more detailed and accurate manner. So it's a little early to be talking about some of the results from the Webb Telescope. The first pictures, I think, only came out something like August or so, after it had been up there doing its
Calibrations
and whatnot. So these are sort of preliminary scientific results, and already it's sort of blowing the doors off of the whole field of astrophysics with its pictures and some of the data that can be gleaned from pixel peeping. Those of us who do astrophotography talk about discerning information from single pixels or small groups of pixels. And instead of leaf peeping, it's called pixel peeping. So we've got some pixel peeping going on for the James Webb Space Telescope. So I thought I'd give a little bit of information about why do we have a space telescope. The blue circle there at the bottom, the blue donut circle around that small dot at the bottom, that is the size of the James Webb Space Telescope mirrors collectively compared to other telescopes. So somewhere, I apologize, the font in this picture is relatively small, but somewhere in there is the Hubble Space Telescope. I think, let's see, the Hubble's actually covered up a little bit by the edge of that blue ring. I'm sad to say, but we have other telescopes, including the giant Magellan Telescope and the Kitt Peak Telescope, a couple of planned telescopes, a 30-meter telescope, etc. And if the Webb Telescope is relatively small compared to some of these earthbound telescopes, then why do we even need it? We've got much bigger telescopes here. Well, we have this very unfortunate part of our planet, at least if you're an astronomer, a very unfortunate part of our planet called the atmosphere. And some of you may like the atmosphere. I can understand why, I think, but here's an example. This is a picture of, I think this is Neptune, and it's a picture taken from a ground-based telescope. In fact, the composite 4-mirror telescope called the VLT, Very Large Telescope. So the Very Large Telescope can take the picture of Neptune, and it's very fuzzy. It's the picture you see up there on the left.
On the right.
Or on
no?
the right. Is it on the right? Yeah, the fuzzy one. Yeah, on the right. Thank you. And recently, in the past 20 years, 30 years or so, and including up until current times, astronomers and opticians and electronics experts and all kinds of experts from different fields of engineering and physics and optics have pooled their brain power and developed some systems called adaptive optics. And adaptive optics are little actuators like you have in a speaker, you know, a speaker in your car or in your house or in your television. It's got a little magnetic coil, and depending upon how you run electricity through that coil, it makes the actuator, or in this case the speaker, go back and forth, and that generates sound waves. Well, imagine plastering thousands of those little actuators, those little audio actuators, on the back of a somewhat flexible telescope mirror. And that's what they do with some of these large telescopes. They, in real time, with something like 1,000 times a second, they can deform very slightly the surface of that mirror, something like a half a wavelength of light, tiny little variation in the surface of the mirror. And then they look at a star, and sometimes they even use what's called an artificial star. They'll shine like a sodium laser or a laser up into the upper atmosphere, and I think sodium ions in the atmosphere fluoresce. And that fluorescence creates an artificial star. Well, they know how bright the laser beam is and how bright the reflection of a laser beam should be from the upper reaches of the atmosphere. So they use that to calibrate the wiggle that you see in stars. So you talk about twinkling stars. Well, the reason stars are seen to twinkle is because they have essentially a point source of light, and that point source of light goes through different layers of the atmosphere. Like you see heat waves in a mirage coming off of relatively warm pavement and whatnot. Imagine those layers of slightly distorted optics piled up for several miles above your head. And that's the reason stars twinkle, is because our atmosphere interferes or bends and warps the light. So no matter how large your telescope is, it's this effect of the atmosphere is called diffraction limiting, right? There's a limit to the resolution. So up until about 20 years ago, no matter how large a telescope you built, you could only get fuzzy pictures once you zoomed in at a certain level. And this applied whether or not you had a little backyard telescope with a 10-inch mirror. In fact, that's kind of the limiting factor. If you have a 10-inch home telescope, then it doesn't matter how much bigger a telescope you make, you're never going to get a better resolution than your 10-inch telescope, even if you have a 200-inch telescope, such as the one on top of Mount Palomar in California.
Is this basically for visible light that you're talking about?
Right.
All this applies to visible light, it doesn't apply to ultraviolet or infrared?
Infrared, right.
Yeah.
I'll talk a little more about ultraviolet and infrared in a minute, Mike, so okay. You're right on top of things there. So, why build a big telescope on Earth at all if you can't get a sharp picture of something because of the warbles in the atmosphere? Well, it's because a large telescope has benefits besides high resolution. And the primary benefit, and in fact the motivating benefit for building huge telescopes prior to about 20 years ago, the motivating inspiration was that you collect more light, and so you can see dimmer objects. The further away something is, the dimmer it looks. And if you're trying to look for a distant galaxy, for example, you need a lot of light gathering power. So the most distant thing, there's some people with really acute night vision can see beyond this. There's a galaxy that's a little further away than the Andromeda galaxy that you can just barely make out in a perfectly dark sky with the unaided eye. But for most people, the furthest thing you can see in the universe with your eye, which has a telescope about that big, right? The little lens in your eye. Even using that tiny little telescope built into your eye, you can see an object in outer space that's about 2.5 million light years away. And that's the Andromeda galaxy. And if you blow up the size of your telescope from a couple of millimeters to 10 inches, and you can use a relatively large telescope that has many thousands of times the light gathering power, then you can get a good image. You can view the Andromeda galaxy more prominently through that telescope because you're collecting a lot more light from it. So you can look in the eyepiece and you can see a fuzzy smudge. Well, once again, you look in a giant telescope and you'll still see a fuzzy smudge. So the limiting, or the diffraction limited resolution of ground-based telescopes has been a perennial problem up until this adaptive optics technology that I talked about. And there's a couple other mechanisms for doing these adaptive optics. So now we've got giant telescopes that collect a lot of light so they can see dim objects, and we have adaptive optics that allow us to get even higher resolution because we correct for the twinkles introduced by the atmosphere. So why do we need a space telescope? Right? Why did we just spend billions of dollars building the James Webb Space Telescope to throw up high? Well, one of the reasons is you can get kind of a head start on overcoming the deficiencies of the warbling of the atmosphere and the way the atmosphere interferes with twinkling stars and even the images of distant galaxies and planets. You can overcome that by getting above as much as the atmosphere as is practical. Well, in the case of terrestrial telescopes, that means building a telescope on top of a mountain. So most large telescopes these days are built on mountains, most optical telescopes. Interestingly enough, radio telescopes are often built in deserts, on flat, low places on Earth. And that's because it's dealing with different wavelengths of light that have different distortion responses to going through the atmosphere. Most radio waves are indifferent to an atmosphere. There I go anthropomorphizing physical things again.
I was thinking that.
Yeah, you were going to call me out on that, weren't you?
No, I was going to let you get by on that one.
Oh, nice of you. Anyway, so if you have an optical telescope and the atmosphere is causing all the warbling, well, if you make your telescope up on a mountain, you have less atmosphere to deal with. So putting a telescope up high is one of the responses to the interference of the atmosphere that has been done for more than a century. So the Mount Palomar telescope is on top of a mountain. The Kitt Peak telescope is on top of Kitt Peak. Mauna Kea in Hawaii has telescopes on it, right? And you try to do that so that you can get above the atmosphere, and in some cases above the weather too. You'll notice the clouds are below this telescope in this picture. So can you extend that to the idea of putting a telescope in space? You put it way beyond the atmosphere. That way you don't need any adaptive optics, but your telescope costs a few $1 billion. Well, there are other benefits besides just getting above the atmosphere and negating the effects of the warbling. And that is because our atmosphere doesn't just distort light, it absorbs light. It absorbs ultraviolet light and it absorbs most infrared light. So on this slide, you see the rainbow there in the hump of the graph on the upper left. And that rainbow denotes the spectrum of visible light from deep purple to blue to, Roy G. Biv, down to green and red. And then on the bottom of this graph, the bottom of this slide, is a graph of the absorption introduced by molecules in our atmosphere. Right? Our atmosphere is mostly nitrogen, and it's got some oxygen and a little tiny bit of carbon dioxide that will probably ruin our planet. and it's got other molecules as well, argon and whatnot. And all of those molecules have a tendency to vibrate when excited. Chemists and physicists literally call it excited by incoming light or incoming radiation. So when the radiation of a particular wavelength hits a particular species of molecule, the molecule vibrates, or in some cases splits apart, etc. There's some complicated what's called photochemistry that happens in atmospheres, and it all involves absorbing light. It just so happens that our atmosphere is pretty good at passing visible colors of light. You'll see the big, on the bottom, you can think of that as a filter. The higher the gray area, the more light is absorbed in that particular range of the spectrum. And you see that visible light essentially makes it through with very little absorption through our atmosphere. But you get up into the ultraviolet region and the absorption is significant. And then you get below the visible spectrum and to the infrared, and our atmosphere, except for a small slice of the spectrum, the infrared spectrum, infrared light is essentially absorbed by our atmosphere. Even if you're up on a mountain, there's enough atmosphere to do damage, to absorb and attenuate the light that you'll be getting. So we have, scientists have, I didn't play a part in this, it would have been fun, but I was busy doing other things at the time, like cooking and entertaining guests. We have different satellites and telescopes that are purpose-built to receive information from different parts of the spectrum, the electromagnetic spectrum. So we have gamma-ray telescopes, we have X-ray telescopes. There are telescopes that can detect photons from ultraviolet light, certainly a few that do visible light. So, for example, the Hubble Space Telescope can do some ultraviolet, certainly visible light, and a little bit into infrared. And then there in the middle of the picture, at the bottom, you see the spectrum covered by the James Webb Telescope. And it does just a tiny sliver into the reddest part of what we call visible light, but a huge amount of infrared light. And then we have other telescopes like the Spitzer Space Telescope that does far infrared. And then from the ground, because you don't have much attenuation, you can do microwave and radio telescopes. And the microwave, the cosmic microwave background you may have heard of, discovered by Penzias and Wilson in, what, 1964 or something like that. That was from using microwave telescope. So the whole spectrum of electromagnetic waves, from gamma rays to radio waves, can carry information to us about astrophysical processes. You know, what color is a star? How bright is a star? These are all things that we gauge by looking at the color of light. And not only that, because of the chemical processes that I alluded to earlier, different astronomical denizens have particular atomic and molecular signatures that they imbue the light with. And so that light could travel for billions of years. How does Carl say? Billions and billions of years before it gets to your telescope. And all that time, information about the way that thing was operating, the physical and chemical processes relevant to that object, is preserved through billions of years of travel and billions of light years of distance. And by the time we receive it on Earth, we're getting a signal from a distant universe, or a distant baby picture of the universe. Well, there's another fascinating thing that happens to light because it's traveling through an expanding universe. So some of you may have heard that our universe is expanding. That's good for real estate agents and those of you looking for more space, because more space is actually being created. Right? It's not, there's a misnomer, a couple of misnomers that I like to take any opportunity to correct that is often made in public discourse about science and the expanding universe. One is that the space we have is expanding. All right, so think about, you've got a limited amount of rubber band and you're just stretching it, and eventually, I mean, isn't the rubber band going to snap, right? Don't you just have a limited amount of rubber to work with? Well, in the context of expanding space, you actually get more space as time goes on. So one of the best ways to visualize this, there's a couple. One is raisin bread. You put some raisin bread dough in the oven, and the dough rises, and the raisins get further apart as the dough rises, because there's more bread in between them, right? It's almost like bread is manufactured by the heat. Now, this analogy, like almost every physical analogy, has its limits, right? You're just stretching the hydrocarbons in the dough and filling it with gas and whatnot. So the analogy breaks down. There's no gas being created to puff up the universe. But more space is created as time goes on, as the universe expands. That's one thing. The second thing is you'll often hear that light is stretched because the universe expands. That is a simplification that can be misleading, right? You see, you'll see all kinds of books and programs that say light is redshifted because the light is stretched by the expanding universe. Well, that's not exactly true. The reason that things look to be redder, the reason that, like the Doppler shift is called a cosmological Doppler shift, right? You're familiar with the trains going by. Some of you have probably heard this analogy. A train's coming at you, and it's got a high pitch, and then it goes past you, and it's got a low pitch, and it sounds something like, right? Well, that same kind of pitch shift happens to the frequencies of light. So if a light source is traveling toward you, then it's blue shifted. So these chemical signatures that you can find in the radio waves, like these absorption spectra from our atmosphere that I talked about, they'll be shifted towards the blue because the light source could be moving toward us. If it's moving away from us, those absorption spectra will be, or emission spectra will be shifted towards the red. Well, in an expanding universe, there's more space being created, typically between galaxies. So stars and planets and whatnot within a solar system or within a galaxy, you can think of them as kind of annealing the fabric of space-time, so that the space-time local to a galaxy isn't puffing all the galaxies up and blowing the galaxies apart, right? But in between galaxies and intergalactic space, that's where the effect of more space being generated as the universe expands becomes ever more pronounced. So these light beams originating from galaxies at the beginning of our universe and the beginning of the time after the Big Bang, they're traveling through space, and over the course of billions of years, more space is being generated. So there's a lazy way to say this, which is the light is stretched as space expands. Well, once a photon of light is emitted, it doesn't change unless it's absorbed and re-emitted by something else. So what's really happening is an effect of relativity, Einstein's theory of relativity. And that effect is we're measuring things in our local universe with the properties of the space-time that have evolved for billions of years to give us the context that we experience with all of our measurements and all of our optical devices and everything. We're using our current context and the local pieces of equipment we have accessible to measure effects that were generated by a universe that was in a much different space-time context. The context of the early universe had things much closer together and much less space-time, and because we're looking with our, like the glasses that we're wearing today in our evolved 13.8 billion year old space-time, and we're measuring things that were generated 13.8 billion years in the past in a different space-time context, it's the comparison of those space-time contexts that makes us measure things differently than we would if that same atom or molecule of CO2 were to emit light today versus 13.8 billion years ago. So it's a relativistic effect due to the way space-time changes. If you instead you say it's because the photons lose light as they travel in their stretch, lose energy as they travel in their stretch, then it begs the question, or it immediately causes you to ask questions like, well, where did the energy go? Are photons of light doing work on space to make space expand? I mean, what happened to the energy of the light particles as they traveled through space? Where did it go? If the light expands, that means the energy decreases. This was what Einstein won the Nobel Prize for, was it finding the way that the energy of light was proportional to its wavelength. If the wavelength expands, where does the energy go? And one of the ways that physicists and astrophysicists get around that is saying, well, the conservation of energy doesn't apply to cosmological things. Well, it kind of still applies, it's just that it's harder to talk about measuring different contexts of space-time. It's like two observers moving relative to each other. The same kind of weirdness happens with special relativity, but this is an effect of general relativity and the changing scale factor of space-time. So, next time you're at a cocktail party and somebody talks to you about the expansion of space and stretching light, you can say, oh, it doesn't really stretch the light, it's just we're measuring it differently because we're in a different relative domain of space-time. All right, now what's all of that for? Why did I tell you all that? Because this cosmological redshift, which is an accurate, short way to talk about the way that light has changed, the perception of light and the reference frames have changed to allow us to see things that look to be redshifted. The cosmological redshift means that species of atoms and astrophysical processes that occurred billions of years ago, when we receive that data today with our various telescopes, it will all look to be redshifted. Right, it is redshifted, but again, it's not because of a simplistic explanation. Well, if you're looking at a distant galaxy that's 12 billion light years away and 12 billion years ago in time, then you've got two effects going on. One is the universe was much more immature. So we would expect the galaxies to look different because the universe wasn't very old at the time. And the second effect is that because of the cosmological redshift, we'd expect them to be redder. So the first stars in the universe are hypothesized to have been brilliant blue and ultraviolet stars that had very brief lifetimes. And they were made of hydrogen and helium and nothing else. And then these stars lived for about 200 or 300 or 500 million years, which is a tiny, tiny fraction of the amount of time that our sun will live, which is about 10 billion years. So these brilliant blue ultraviolet stars, when we see them with our telescopes today, they're going to be redshifted into the infrared. So even though they were brilliant and blue and blazing bright, we see them as little red smudges. That's a reason to have a space telescope, because all that infrared light from the early universe would be absorbed by our atmosphere. So if we want to investigate the early universe and the formation and the lifespans and the chemical properties of the first stars in the universe, we need infrared telescopes. And that means getting above the atmosphere. So we've got the James Webb Telescope and the Hubble Telescope. Again, Hubble can do a little bit of infrared, but not the deep infrared. And this slide compares some of their physical characteristics. All right, this is delightful. This is a picture of a planet. So before we start looking at the, quite literally speaking, before we look at the distant early universe, let's see what James Webb can do with some things nearby. This is a picture from the James Webb Space Telescope, JWST, of the planet Jupiter and some of its moons. This is incredible. I mean, the Hubble Space Telescope could not approach this. The larger the mirror out in space, the larger the mirror, the better the resolution. You're not limited by the atmosphere. So not only do you gather dimmer light by having a large mirror, but you also can zoom in more in common parlance. You get a better, higher resolution picture. So this is a picture that Webb took of the planet Jupiter. And look at the detail. This is amazing. I mean, we've got pictures now due to space probes like the Galileo probe and whatnot that traveled out to Jupiter and took close-up pictures. But this is a phenomenal picture to be taken from an object that's only a couple million, or what was it, Mike? Do you remember, like 1.5 million miles away from Earth or something like that?
Jupiter?
No. The
The Webb telescope. I thought it was about 1 million miles away.
1 million miles away, yeah. And not only that, it can see Titan, one of the giant moons of Saturn. And it can see clouds moving on Titan. Amazing, amazing science that we can get. And because it's infrared, it can see through the haze of the atmosphere of Titan and uncover some of the lower atmospheric phenomena. You can make time-lapse films of the weather on Titan, for example. That's one of the things that Webb is capable of. Here is, I forget if this is Neptune or Uranus. I think it's Uranus. I apologize if I got that wrong. The planets Uranus and Neptune look very similar. One of them is more bluish and the other is more greenish. And I apologize for forgetting which is which. But in any case, I believe it's Neptune has a ring system. And here in the infrared from the Webb telescope, you can see clearly the slightly heated particles of ice that constitute the ring system of Neptune. Here's a Voyager. First there on the left is a Voyager flyby picture, and then you can see the Hubble picture, and then you can see the Webb picture, which again, infrared radiation is emitted by things that are hot. So you take a regular molecule and you jiggle it around, that is heat, right? Heat is molecules and atoms moving, and that heat can be and is dissipated as thermal radiation in the infrared spectrum. And then if we zoom out, we see that same picture of the planet in the context of the wider universe. And there it is with, I think, Triton, its large satellite, and some of the other smaller satellites nearby. And then here's the whole field of view. This is the picture that Webb took that we zoomed in to get the close-up picture. And if you look down in the lower left, you can see a galaxy photobombing the picture. And that is a common occurrence. You have nearly any picture from the Webb Space Telescope, and you'll see galaxies in it. All right, that's all I'm going to say about nearby planets. Webb has also been used, again, it's only been out there for a year and only been taking scientific data for a few months, but there are some preliminary amazing results. So the animated graphic there shows an exoplanet moving around a distant star. And this planet, as it moves in front of the star, slightly diminishes the light of that star. That's the animated plot there showing the light intensity from that planet. Well, if you've got really good resolution on your telescope, you can notice when the atmosphere of the planet reaches the edge of the star's starlight region, and you can pick apart the chemical spectrum from the light that just sort of glances through the atmosphere around the exoplanet. And this pointillistic looking graph, the large graph there on the bottom of this, shows the chemical signatures of the gases in the atmosphere of a planet that's thousands of light years away that Webb was able to do. It was also the first example of photochemistry on an exoplanet. We know, physics is physics. Things that happen in our atmosphere and in the planets of our solar system's atmospheres will happen in other planets, but this is the first direct evidence of photochemistry happening in another planet's atmosphere. So you see water vapor and the signatures of other chemicals there in this, and that will, this capability over the coming decade or two of the lifespan of the Webb telescope, as it looks at other exoplanets, should be able to tell us interesting things like, is there oxygen? Is there appreciable oxygen in the atmosphere of an exoplanet? And other than the photodisassociation of water molecules, the only other plausible mechanism that anyone has been able to imagine for there being oxygen, free oxygen in an atmosphere, is the respiration of life. So, really interesting stuff that we could potentially find from exoplanet atmospheric chemistry that we can do with the Webb telescope.
If you're looking at those, the picture showing the moon or that satellite transecting, going across the face of that faraway star, that's maybe an artist's conception of this, while
Yeah.
the other actual data that tends to prove what's actually happening there, right? There's a reduction in data coming in, resolving itself to be the fact that something has to be interfering
Right.
with that data getting to us.
Right, the line graph that is being drawn there, that is real data received during a transit event. The animation of a planet, of a little black dot moving in front of its star, that's just an artist's interpretation of the data. But there is no other interpretation that is consistent with with that data and other data that we've received. So that is a physically real process that happens. But the Webb telescope, as powerful as it is, it can't zoom in on a star with high enough acuity that it gives the star a surface area and directly detects it as a disk. So, a couple of nearby stars, there'll be an exception to that, like it should be able to make out some features on Betelgeuse. Right, so, you know, exoplanet systems can be extraordinarily diverse, vastly different than anything we observe in our solar system. You can have magnetically active red dwarf stars that have coronal mass ejections of plasma and streamers of high energy particles that put the solar flares of our sun to shame. They're more frequent, they're more powerful, and then you can also have planets near those stars that orbit with a period of a few hours, and the chemistry and the magnetic interactions are as varied as the laws of physics allow. And so exploring the dynamics chemically and physically of exoplanet systems will be a really rich field. And there are other telescopes that are being planned, space telescopes, to really specialize in this kind of thing, but the Webb will get us started. All right, let's move on to dead stars, one of my favorite topics. So on the left is, I think that's a Hubble picture of what's called a planetary nebula. So when a star like the sun eventually runs out of fuel in its core, then it starts briefly burning helium instead of hydrogen. It runs out of hydrogen. Helium burns at a higher temperature. It's compressed more in order to get it to burn from a nuclear standpoint. So the star gets hotter and puffs out, turns into a red giant. And eventually it puffs out so much that it starts ejecting the outer layers of the star, and this forms a bubble of ever-expanding material. And it forms what are called planetary nebulae, which are some of the most beautiful objects in the night sky. And this is a particularly strange planetary nebula where it seems to have a lot of whorls and bubbles within bubbles and a lot of complexity going on. So it's not just a star that died and blew a bubble, but something odd was happening here. And so largely using the Webb telescope data, scientists have been able to piece together the murder scene of this star, and they found that the star that generated this chaotic mess of spaghetti, tangled gases, was not isolated. There were 4 other stars involved in this dynamic waltz, and part of the waltz involved a star getting really close to the one that emitted these streamers of gas, and it essentially prematurely ripped the star apart. And then you can find some of the Webb telescope has allowed us to see some of those other stars whirling around inside this nebula. So it's a family of 5 stars that had a complicated dance of doom that shredded one of them.
Now, these are enhanced with a filter. They're taken with ultraviolet infrared light,
Yeah.
and then the different wavelengths that are detected are then maybe colorized by
Yeah.
a computer.
Right.
So this is just a colorization that tends to give you an indication of different wavelengths of each of those.
Right. One of the sad realities that is not consistent with our science fiction portrayal of the universe is, even if you were flying relatively near this object in space, you wouldn't see anything, right? Because the gas is so diffuse and the light is so dim that even if you got really close to it, your eye wouldn't be able to perceive much. Maybe you'd see a dim halo around the star where the nebula is, but by using a telescope that can integrate a lot of light, capture light for a long time and make something that's dim, inherently dim, gather more signal for it to make it brighter, if you will, in a photograph. It really enhances what we can determine about the physical processes. And in this case, because it's receiving infrared light, they swap out different, they kind of do, not exactly one for one, but they take the infrared spectrum and they just shift it into the visible spectrum and then apply the visible colors to highlight what the dynamics and the color variation, at least, the light frequency variation would be in that object.
But it's not arbitrary, too. There is data or information given, so when you see the yellow portion of that, all that yellow portion is having certain similar characteristics to all the other yellow portion in
Right.
there. So it's still giving you data, like you say, if it's shifted to an area where we can see it better, we can compare and contrast and
Right.
look for differences or similarities.
Yeah, you can certainly pick out, the different species of molecule have infrared spectrums, and I think Joanne knows this with intimate detail probably, but things like sodium and O2 and CO2 and whatnot, they have infrared as well as visible excitation spectra, and you can use that to identify the different species of molecule in these things. All right, let's move further away in the universe. Here's a section of the sky, Centaurus. You see the little scorpion tail down there in the lower right. This is a section of the Milky Way. Up above are some other constellations. So when you look at the night sky, you'll see all these figures. Well, if you do it in the right computer program. I see the same thing back there that you see up here. Oh, looks like it's really bright. It's kind of washed out. Yeah, I don't know. Mike, is there a light switch that can...
Maybe I can do something.
I don't know if the light switch is up here.
No, I think they're back here.
Okay. Those of you online, I suspect Dave is zooming in on that so that you can see it well. Oh, that's better. Yeah, that's a lot better. Okay. Is anyone scared of the dark? No? Okay. I used to be scared of the dark, and then I fell in love with the stars. So. All right, so this is an image. I think you'll probably just leave it that way, Mike. There's going to be a lot of dark pictures. All right, so this is an artist's impression of the mythological figures that we have imagined being represented by asterisms, patterns of stars. And this particular set of asterisms or constellations zoom in to an area near what would be the central bulge or the heart of the Milky Way galaxy.
What's that word, asterisms?
Yeah.
I haven't heard that one used before, but constellations imply something man-made, imposed upon it because it has a certain picture
Yeah, connect the dots
associated
or
with it.
something. So an asterism, like the southern teapot in the summer sky, there's no constellation called the teapot, right? Or the Southern Cross, right? There is no constellation called the Southern Cross, but these are names for what are called asterisms. So people across generations have noticed particularly brilliant and sort of self-contained groupings of stars, and they give them names. Well, that's the teapot, that's the summer teapot, right? Well, a constellation is nothing but an asterism that has a more formalized name. And in my book, I talk about constellations and how they got their names and some of the names that have been passed down from the Greeks or before. And there's a wonderful, I haven't written about this, but there's a wonderful story about the Pleiades called the Seven Sisters. But if you go back even 20,000 years and you apply retroactive astrophysical knowledge to the way the stars work, the Pleiades were never visible in the past 20,000 years as 7 stars. They were visible as 6. So why are they called Seven Sisters? It may be a hint passed down through thousands of human generations, starting in prehistory, of when those stars had a slightly different arrangement, and you could see 7 of them instead of 6. So that may be an echo of something in our deep ancestry as a human species that is engraved in our naming of the Pleiades. So anyway, that's a cool thing about, you know, we see the night sky and we impart our mythology to it, but they're just asterisms. They're just connect the dot things that we can imagine in the sky. But this, again, this looks towards the heart of our galaxy. This is constellation Sagittarius. And if you zoom in on a portion of it with a telescope, so the telescope that I own and the astrophotography equipment that I own could take a picture like this, maybe even better than this. I'm just saying it could be better, it could be the best. You can take pictures through a backyard telescope that show you these clouds of gas and dust that are common as you get towards the heart of our galaxy. And here's a picture, I think this is from, I don't have the proper credit on this. This is one of the big European space telescopes, might be the one in Chile. And this is not Chile, the Canary Islands. And this is a picture from a professional telescope of this same region. You see,
Wow.
you know, billions of stars and these clouds of gas and dust. Within these clouds, new stars are being born.
So these have all been land-based.
Yeah, this
Photographs,
is a land-based
yeah.
telescope. So I'm comparing what you'd see sort of with a backyard telescope, with a good professional telescope, and another image of a good telescope. And then you can take this one part of the picture and you can really zoom in on it. And when you do that with something like the Hubble Space Telescope, you see that bright starburst region in the center of that one nebula is a knot, a tangled knot of baby stars. And then you zoom in a little more on this region here where I put the blue circle. And when we zoom in on that, we see this. Now, the little cutouts in this are sections where the Hubble telescope has taken smaller scale, zoomed in pictures of some of the features in the center of this giant nebula. So these are areas where new stars are being born. And then we can zoom in on one of these, and this has been given colloquially the name the Pillars of Creation. So again, let me go back. So you can see the whole nebula here. We zoom into it. The Pillars of Creation are kind of right there in the center in what's called the Eagle Nebula. And then you zoom in on those. And you know, we've got space telescopes and better telescopes, so let's really zoom in on this Eagle Nebula. This is a 1995 picture taken by Hubble and visible light. And you've got gases evaporating, as it were, around baby stars that are created in these dark knots of gas and dust. And you can zoom in on a portion of it. And this is again the Hubble picture. And then this is a more recent Hubble picture with some better instruments. Hubble can barely see into the infrared. This is an infrared picture from Hubble. And then we get the James Webb Space Telescope zooming in on this. So you can compare the Hubble picture on the right with the James Webb Space Telescope. Because it has further reach into the infrared, it can extract more details about the dynamics of the gas and dust that are occurring in this region. And this is really zoomed in. And stars are born in darkness. In order for gas clouds to collapse enough to form a star, they have to cool off, they radiate thermal energy, and the gas clouds become very cold before the star is born. And cold things don't emit light, so they're dark. So dark knots, dark filaments are clumps of cooling gas, in the center of which could be baby stars.
But when you say they don't emit light, are you saying visible light or light of the infrared spectrum as well?
Yeah, they get cool enough that, in fact, the coldest known place in the universe, but we can only see a tiny fraction of the universe with any fidelity. But the coldest known place in the universe is one of these called Bok globules, B-O-K globules. And it's you can see, if you look up there, you can see these dark ropey filaments, and that's compressed cooling gas. And inside of those, I can't guarantee it, but it's scientifically plausible that inside those filaments are protostars where the gas is cool enough to collapse. It's lost enough energy through thermal radiation over millions of years that it collapses to form a protostar. So really interesting things about the way stars are born and they die. I talked about the dying star. All of that information can be garnered from some of the light and the infrared signals emitted by these things in space, and the Webb telescope will help us understand those better. Here's a picture of a nearby galaxy. This is a fascinating galaxy. Gosh, I wish I had another hour. This galaxy is one of the most ancient galaxies we've ever detected. And because of the way subsequent generations of stars recycle elements, and they have a kind of alchemy where heavier elements are synthesized by the gas and dust that gets blown off of early stars, you can kind of gauge how old a collection of stars is by looking at the chemical elements in it. And this particular galaxy, let me zoom out again, this particular galaxy is a dwarf galaxy near the Milky Way, and the stars in it are so old that astrophysicists think that it has never interacted with any other galaxy. It's been a self-contained raft of stars since the beginning of the universe, or near the beginning of the universe. And if you zoom in to this ancient relic of the baby universe, which happens to be in our backyard, if you zoom in with a regular telescope, you'll see that this is as high a resolution a picture as we can get. So those are individual stars within that relic galaxy. And then we point the Webb at that same area.
My goodness.
So using the Webb, we can get more information about the population of stars, the chemical makeup. We can extrapolate back about the history that this dwarf galaxy has undergone. And then if you look closely, it might be hard to see in this picture, but if you look closely, you can see galaxies. So like I said, nearly every picture taken by the Webb telescope is photobombed by galaxies, including this dense agglomeration of stars that's a nearby dwarf galaxy. We can peer into it with such high resolution with the Webb telescope that we can make out galaxies that reside behind it.
And again, this is a portion of the sky by the time you get to there that you,
Like a grain of sand.
yeah, you would, yeah, it's so tiny you would cover it up completely plus more with just your pinky over that portion of the
absolutely.
sky.
Yeah. Speaking of galaxies, here's a beautiful galaxy that has been pierced by a smaller galaxy, kind of like that ancient galaxy that I just showed you. This was started as a regular spiral galaxy, and the heart of it was pierced by a bullet in the form of a small irregular galaxy that zoomed through it. Interestingly, when galaxies collide, stars don't collide, right? The gas in this room, the oxygen in this room, the distance between molecules of oxygen and carbon dioxide and nitrogen, the relative distance between the molecules compared to the size of the molecules is something like 15 orders of magnitude closer in relative terms than stars are to each other in a galaxy. So a galaxy is mostly empty space. So when they collide, the gravitational effects cause a warping of the overall geometry of the object, and the shock wave that results can compress gas in the galaxy and initiate star formation, but you don't get stars literally bumping into each other even when galaxies collide. But on the top is an optical image of this so-called cartwheel galaxy, and on the bottom is the Webb telescope image, highlighting in red these areas of new star birth that were instigated by the shrapnel of the galactic collision. And here's another instrument on the Webb telescope that really highlights areas of star birth near the core and then in the outer reaches as the shock wave propagates out from the center over millions of years. They've been able to figure out the culprit, the bullet. It's that distant galaxy off to the right. And then using radio telescopes on the ground, they've mapped out the stream of plasma and hot gas that traces the trail of that galaxy that pierced the spiral. Here's a distant galaxy cluster. This is called SMACS for Southern Massive Cluster Survey. So this is in the southern sky. And easy to remember name, J0723, etc., etc. And here's how they come up with those names. They look at the celestial coordinates, which are kind of like latitude and longitude, but projected onto the sky. I won't get into details. But using those coordinates, that's how they come up with the designation for this. So it's just its coordinates in the sky. But again, here's the Hubble telescope view. And here is the Webb telescope view. Astonishing clarity. Each one of those dots, with a couple of exceptions like that, the thing in the middle that's super bright and has those diffraction spikes, that's a star in our local galaxy that is photobombing a field of galaxies. But otherwise, I think nearly everything in that picture is another galaxy.
And what's the refraction pattern?
Yeah, the spikes, the 1, 2, 3, 6 spikes is because of the hexagonal mirror shape of the segments of the Webb telescope. And if you look closely at this, you'll see galaxies that are kind of smeared out into arcs. That's because the galaxies in the center are, in relative cosmological terms, close by. They're about 4.6 billion light years away, but the distant red smears of galaxies are much further away, something like 10, 12 billion light years away. And this is a 12-hour exposure. Remember a couple years ago I talked about the Hubble Ultra Deep Field, where the Hubble telescope gazed at a patch of sky about the size of your fingernail held at arm's length. and it gazed at that same patch of sky off and on for a cumulative time of about 30 days. This is 9 hours with the Webb telescope. And over time, the Webb telescope will look at some of these distant fields that are not very obscured by stars and gas in our own galaxy. They'll look at these distant fields and accumulate ever more light and ever more information about what's going on out there in the early and distant universe. This field of view from the James Webb Telescope is about the size of a grain of sand held at arm's length.
Wow. And to get that clarity in the reception of the
Yep.
data, right? Out of a grain of sand.
And there's the comparison between Hubble and Webb. All right, talking a little more about distant galaxies. One of the other things you can see is the most distant galaxies ever measured by humans. So we have really good evidence from many different studies looking at many different aspects of the universe, chemical, geological, astrophysical, etc., that converge upon the same answer that the universe is about 13.8 billion years old. So can we see, literally, can we see the first stars and the first galaxies? And astrophysicists denote distance in time and space with a factor they call the Z factor. And that corresponds to the amount of redshift, cosmological redshift, due to the difference between today's space-time and the space-time when the light was first emitted. And these Z factors push the date back further and further and further until just this week there was a news story about some galaxies that the Webb had taken photographs of that are only 400 million years after the Big Bang. So the Big Bang was a particular point in time when the universe started expanding violently. I've given talks about that. I'm not going to go into detail now. But these first galaxies ignited something like 200 million years after the Big Bang, according to theoretical models. And the Webb telescope has already been able to take pictures of galaxies that are 400 million years after the Big Bang. And some of these are showing the expected and predicted effects of ionizing the primordial gas of hydrogen and helium that would have cocooned and cocooned the galaxies and suffused the early universe. And so the light signature of some of these early galaxies are showing that it's called the age of reionization, when shortly after the universe became transparent to visible light. There's complicated science around that I've talked about in the past as well. And then here is one of the most recent pictures of accumulated pictures stitched together of a portion of the sky that is relatively blank and uninteresting if you look at it with a regular telescope. But when you look at it with a space telescope attuned to the infrared, you see that the distant sky is just littered with galaxies. This is a survey called Pearls, and it's about 2% of the size of the full moon. And the full moon's only about the size of a dime held at arm's length, right? If you actually go outside and try to figure out how big is the full moon is pretty small in the scope of the expanse of the night sky. And this is a picture of an area of the sky that's only 2% of the size of the full moon, and there are thousands upon thousands of galaxies. A profligate amount of material. Amazing stuff. And each of these galaxies could have its own population of stars. We could potentially see the way Stellar dynamics and stellar evolution have caused different light to be emitted from different galaxies at different ages. And the number of galaxies that we can look at now and study, do a statistical survey to find properties of ancient and distant galaxies. The number of those available for analysis has literally exploded. Well, not literally exploded, but you know what I mean.
Figuratively exploded.
Figuratively exploded. Thank you, Mike, for that clarification. All right. So when we're looking back and out at the early universe, we're seeing different epochs. And the Hubble telescope gets us so far. That's the top arrow there. If it's hard for you to read, that arrow extends back in time towards the Big Bang. And that's about as far as Hubble can see with its picayune reach into the infrared. But we expect the James Webb Telescope, with a long enough exposure, to be able to send us data about photons that were emitted from the infant universe shortly after the cosmic microwave background. So the cosmic microwave background ended. That's the end of the orange cone there, and then there's something called the dark ages, where the light was not able to move freely in the universe because it was a hot ionized gas, and light couldn't freely move. And then as soon as it cooled off and expanded enough that light could move through the universe, we might be able to discern some galaxies and populations of stars from that era. Already preliminary results are showing that galaxies might have more structure than we anticipated from that era and be more massive. And one of the implications of that is that supermassive black holes, which are the nucleus of many galaxies, supermassive black holes may have been formed very early in the universe. In fact, they may have been formed by a process that happened very close to the inflationary epoch of the Big Bang. So figuring out when supermassive black holes were generated and how big they were, that's another piece of science that we could help piece together the mystery. And then finally, this is my last slide. I know I've gone a little bit over. One of the ways we denote the distances to cosmological objects is we have what's called the distance ladder. So we look at the distance to nearby stars. Stars are really close to us in cosmological terms. From decade to decade, you can actually see them moving, relatively speaking, across the night sky. And that gives us a parallax method for figuring out how far away they are using simple trigonometry. And then from there, there's a wonderful type of star called a Cepheid variable. And these stars have been discovered to have a pulsing light profile. They get brighter and dimmer and brighter and dimmer and brighter and dimmer and brighter in a very regular manner. But the period of that, brighter and dimmer, the period of that is inherently related to the brightness of the star. So again, I forget, I don't remember if it's a brighter star has a shorter period or a brighter star has a longer period, but the correlation is almost perfect, whichever way it goes. So using Cepheid variables and looking at the spectra of the light coming from it, they can say, oh yeah, that's a Cepheid variable, and then they can see how bright it is inherently by its pulsation. So by measuring how often it brightens and dims, they can say, well, its inherent brightness must be X. And then because something further away looks dimmer, they can then extrapolate back and say, how far away is that star? Because it looks dimmer to us. So that's one of the first rungs in the cosmological distance ladder, and there are others like supernova that always have an inherent brightness and whatnot. And so the whole story is we can piece together a ladder of extrapolations that are each justified by science that helps us understand how far away an object in the cosmos is. And the Webb telescope is going to help us refine the spacing between the rungs on that to get an even better scientific result about the distances in the cosmos. And that's all I had. Sorry, I'm about 10 minutes over, but I hope you enjoyed this year's Cosmic Ornaments.
We have any fast questions or thoughts?
Of course. Did you expect something else? Hi, you were talking about the apparent light shift of atoms. And of course, we see this. I mean, if you look at, for instance, the D line of sodium, the further away it is, the further away the line comes in, because shifted red, 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 red,
Right.
red. And
Cosmologically speaking.
cosmologically speaking, and I'm thinking, this is sort of goes back to Einstein and everything being relative. As far as the photon itself is concerned, it doesn't have any age. It's instantly new. It's as old as it's ever been. It knows about nothing, and nothing has changed as far as it is concerned. So what we're seeing is our perspective of that, which does change with the distance.
Yeah, in my second book, which I've not yet published, I have a section when I'm talking about relativity called No Time for Light. And that's the whole point, is that if you're a photon, nothing changes. There's no passage of time. So how can you lose energy? Unless you're emitted and destroyed, and then a new photon is generated with a different property. So.
All right, well, thanks so much. We hope you have a wonderful holiday season, and appreciate your support of Science Sunday. I think the next thing we're coming up with is we're still in the works for, but it'll be the third Sunday in January. The first Sunday in January is January 1st, and so I think we're declaring a scientific holiday that day. So it'll be the 15th of January to be our next Science Sunday. So thanks so much for coming in, Scott. Wonderful presentation, and yeah, you just think of those beautiful ornaments up in the sky every night and just hanging there for all of us to enjoy, right? So thanks so much. Yeah, a big one.
Thank you.
So I'll be hanging around in the back if you have any other questions.